Okay, today we're going to look at transformations with exponential equations and functions. So similar to what we did earlier in the year with our transformations, stretches, reflections, translations, up, down, left, right, same thing applies to exponential equations. So if we look at this title page, we know that our normal exponential equation should look something like that. So you can see we definitely moved it up, we may have stretched it, and so on. So that's what we're going to be looking at today. So let's go through each component one at a time to make sure you understand it. So this first one, we have y equals a times c to the x. Remember our regular equation was just c to the x, where c could be a 2, a 3, or whatever. So our a value, just like we did before, is a vertical stretch. But with these kind of equations, that vertical stretch is also going to be our y-intercept, because typically we have a y-intercept of 1. So you can see here the 2 in the equation, it moves that y-intercept up to 2. So 2 times 1 would equal the 2. And if we have a negative, same thing applies. Vertical reflection, so it'd go downwards, and we're at 3, so it's 3 down. Horizontal stretches, then, remember that's with the x. So that means we'd have it as an exponent. So you can see here we have a 2 up as the exponent with the x. So just like we did before, again, that 2, remember we have to do it as 1/2. So in this case, this would be a 1/2 horizontal stretch. So our normal coordinate would be, for this equation, would be something like 3 to the 1, which would be at 3, which is right there. And you can see with a 1/2 stretch, we've now moved it over half as far. So we've squashed it inwards. So that looks good. So this other one, you can see we've got a base of a half. So remember, that's a decreasing. The negative would mean reflection. So our regular graph would be something like that. So we did the flip horizontally. Then this in this case would be, your b value would be a 1/3. So our stretch would be then 3 times wider. So you can see that's why our graph gets stretched out really wide. Okay, in terms of translation, same rules as before as well. If it's a horizontal translation, it's going to be up as the exponent as part of the x. So in this case, we got a -2, so that means we went 2 to the right. So you can see our normal graph would do something like that. So we've now moved that point over 2 spots to the right. And if we look at this one, we've got a +3, so that means we went 3 left. So you can see here we've got our regular graph again, and we moved it over 3 spots to the left. Okay, so a lot of this is the exact same thing we did before, so nothing too much changes. Here we got our k value, so this would be outside of the exponent. So we'd have y -2, so that's our 2 down. So you can see our graph went down. It should have been at 1, it's now down at -1, so we went down 2. And here we have y +3, so we've gone up 3. Or remember, with these kind of equations, we could also bring the 3 to the other side. So that's a good way to remember that it's with the y, it's not a horizontal with the x. So if we get an equation that has combinations of these things, this is what the equation would look like. So let's just look at an example. If I gave you 3 times 2 to the 1/2 x minus 3 plus 4. So let's kind of figure out what this is. So the 3 means 3 times vertical stretch. The 2 is our base exponent, so that's our c value. So that doesn't have anything to do with the transformation. That's just saying our standard equation would have been y equals 2 to the x. So that just tells us what we're starting with, and then from there we're going to do our translations. So the 2 doesn't do anything. The half, or that would be 2 times horizontal stretch. And the -3 would be 3 to the right. And the last one, 4 up. Okay, so same kind of thing as before, just a little bit different looking equation. So let's go through these. Here's some examples. So in this case, we want to know what the transformation would be. So in this case, we're going up 3. So in terms of a graph, it would just be our regular graph. But now we're going to move it up 3, so it would be something like that. What's kind of key to remember is, so our original domain was XER. It's still going to be XER. That doesn't change. Our range originally was greater than 0, but if we go up 3, it's now going to be greater than 3. So I don't quite have mine sketched out right. So at 3, we'd have our asymptote line now. So our graph should have actually curled more something like that. Okay, intercepts, original y-intercept was at 1. We went up 3, so now y-intercept would be at 4. And our asymptote, like I said, is at the new location of y equals 3. And I have on here a transformation of xy. So what does that mean is whatever our original coordinates are, if we move it up 4, all we're going to be doing is changing the y coordinate to go up 4 as well. Okay, so this next one we've got 5 to the right. Okay, so our domain and range, nothing would change for those compared to our normal equation. Our y-intercept would be different though, so our original y-intercept was at 1, so we'd have to figure out what the original coordinate would have been when x was -5. If we go 5 to the right, if we put -5 in, that would be 2 to the -5, which is 1 over 32, 1 over 64. So that means our new y-intercept would be at 1/64. And you could do that from your calculator, that's pretty easy. And in terms of our coordinate, our xy coordinate would change into x plus 5 if we're going 5 to the right, and our y would stay the same. Okay, the last one, we got 4 up, because it's written backwards. And we got 1 left. So we're good, so we basically would just do the same thing. Our 4 up, that would change our range, so domain would still be the same. Range would now be up 4, so greater than 4. Our y-intercept would change because we went 1 left, so whatever the original would be, it would be shifted over, and we can leave that. We can figure that out from your calculator if you needed to. And then we'd have our x-coordinate, if we're going for our 1 left, we'd have -1, and then our y-coordinate would be up 4. So here's a couple other ones. Let's try a couple more. So this one, we're doing a 2 times vertical stretch. And that's it. So in terms of this one, our graph would then just be twice as tall. So our domain, once again, would be any real number. Range is still y is greater than 0. Intercepts would still be the same, except it's double now. So our y-intercept would be at 0,2 instead of 0,1. And then in terms of our coordinate, our xy coordinate would go twice vertically, so that'd be x and 2y. And this other one, our last one, we've got 3 to the 2x. So you can see in this case, our 2 is a 1/2 horizontal stretch. So everything would be the same. Our y-intercept would change. Instead of it being at 1, it would be at 1/2 now. And our coordinates would be 1/2 horizontally, and our y would stay the same. Oops, this one I messed up. If it's a horizontal stretch, our y-intercept wouldn't change. It would still just be 0 and 1. Sorry. Okay, let's do one more. So this one has a little bit of everything. So what's the transformations? We've got the negative would be a vertical flip. So vertical reflection. The 4 would mean 4 times vertical stretch. And we got a plus, or 1/3. So that'd be a 3 times horizontal stretch. And I messed up here. The 4 isn't a stretch. That is our base. That's our exponent base. So we wouldn't have any stretching because our number, in terms of the number in front of the base, would actually be -1. So that's just our vertical flip. So vertical flip, 3 times horizontal. We got 2 left and 1 down. So in terms of a coordinate, we won't bother drawing the sketch. You could do that. But in terms of each coordinate, our xy coordinate then, if we're doing a vertical flip, that would change it to -y. And our 3 times horizontal, so we'd have triple the x value, whatever that is. And then we'd go 2 left, so we would go -2, and 1 down, so we'd have -y minus 1. So we could take each coordinate of our original graph and just do those transformations to it, and that would give you every other coordinate. Okay, let's look at one word problem. So this one, it says the average price of a house in Leduc is $400,000. It's predicted house prices will double every 15 years, so we want to know what that equation would be. So in terms of our equation, we would basically say it's doubling, so we should have a standard equation like 2x. But if we don't have a vertical stretch, that means our houses are starting at $1, which doesn't make sense. So that 400,000 ends up being your vertical stretch, or your A value. So that's that part. So now if we kind of just left it at that, that means our house would start at 400,000, and for every 1x or 1 year, it would be doubling. So we'd go 400,000 to 800,000 in 1 year. That doesn't occur. It happens every 15 years. So we actually have to mean our horizontal stretch would be 15. So in our formula, we'd write it as 1 over 15. So that would be our equation we want. So once you have that, you can graph it or whatever. So now for question B, it says, what would your house price be in 10 years? So off your graph, or you could just plug a 10 in for the x value. So 2, 10 to the 15, figure out what that is. And if you wanted 25 years, just put in the 25 over 15 and you're done. So we could figure those out pretty easily. Like I said, you could do it from your graph, or it's probably easier and quicker just to type them in directly. So if we did 400,000 times 2 to the power of 10 over 15, that gives us a house price of $634,960 approximately. And we can do the same thing again for 25 years, and that gives us an answer of 1.2 million. So 1269920. Okay, so 1.3 million almost. So those are the correct ways to work with that equation. And that's all.